I want to give an update based on my last video about the asset variant system and what we're doing to do that. So once again, thank you to Yosh, J4, you, Julian, a bunch of other people. Check the announcements like this. There's really like a growing number of people to thank for this. Compressinator now runs on Linux. That whole thing is done. And so now over on our main Epic machine, it's got an AMD Epic in it. That's why we call it the Epic machine. It's got a Docker container that's running the normal queue, and it's going away nicely. We also have on my local network, we have on Kane, which is the first server that a person called Svekin sent me. So thanks so much for that. It just sits on my bookshelf, and I've got two of them. One's called Kane, one's called Abel. Kane is squirreling away on the poison queue and trying to get that resolved. I had some questions about what the poison queue is, so I've got a nice diagram up here. So there are two queues. There's the regular and the poison queue. Regular, we just process on this Docker container, and images come in, we process them. Another one, another one, another one. If one comes in and it causes an issue, and it keeps causing that issue, and the queue can't progress because that asset's there, then what it will do is it will take these poison ones and it'll put them into the poison queue such that the poison queue can pick them up later. You could also call this like the dev queue or something like that, because it's where we as engineers of Yellow Dog Man Studios need to take a look and figure out what's going on. To try and understand what's going on, that's one of the reasons why I added all these metrics. So I wanted to talk about how they worked a little bit. So I've timed this to last 12 hours, and you'll see here in the middle this cloud queue metrics. This is old. Like, you'll be able to find this over on the regular Resonite metrics one in the center here. But this is just a sort of expanded view of it with our new graphs. So you can see here that we had a big peak of workers here, and we had a corresponding dip in this graph. So what's this graph about? This graph here shows the number of parallelizable like worker units that exist on the Skyfrost Epic machine. We use the action block library system threading task data flow for this, and you'll see that it's got max degrees of parallelization. And what it basically means is every time you post a job to this action block, the function inside it, which in this case is just a thread sleep, but in ours is like a really complicated thing to do all the calculation, it can run this number of simultaneous copies of that operation. So that's what's being shown there. So this number is just the max degrees of parallelization here is the number here, 72. So we have 72 max workers over on the Epic machine, and then this free number will be how many aren't doing anything. I do have another metric that I've just added a new build, which is the number of active workers. That graph will make a little bit more sense. It'll be like an upside down version of this one. Instead of the graph dipping when there's bits of activity, it will spike a bit like this, and then you could lay them up over on top of each other, and maybe I'll do that on another graph. So you'll see like a peak that sort of encompasses this green peak in yellow, and that'll be the workers coming online to kick it off. You also see over here utilization. This is just mathematical percentage maths based on free and capacity of workers. Actually, to peek behind the curtain, you can see how it works. Look, we go into this transformation here. I don't need this top one because I've added some maths to do that on the server side, but it's still here until I update that. But you'll see it's basically active workers divided by capacity. You get this utilization graph. So we could alert on this now. Let's say this goes up to 99. It stays at 99 for a long time. It means like, hey, maybe we need to start another worker because we're at capacity, right? We need more workers. You can actually see that happened here for the space of what looks to be 10 minutes. We were at capacity. That's interesting to know. If that keeps happening, particularly if that happens towards the sort of end of MMC, hey, maybe I'll throw Kane and Abel at it just to get us through that. But that's something we couldn't do before, and I will add up alerts on here later. Moving forwards past that, oh, by the way, we had some questions about what metadata is. So variants are like the actual image data, whereas metadata is like data about the image. And sometimes we need to do operations on that to make it better for our storage. That's there. Moving on from that, you'll see that we have a baseline that just can't seem to go through. It's like a floor, and the floor is around 6,100. Those are poison items. They're not shown separately on this graph. I did want to get that done, but these are poison items on this poison queue, and it means that these are assets which are causing problems, and that we need to figure out what's going on there. This is sort of reflected here as well with the success and failure percentages. So you can see, hey, we've got a 4% failure rate and a 95% success rate, which is quite good if I do say so myself. that 4% is tasks and variants that will eventually make their way into the poison queue, and then they'll disappear from this number, but they'll appear on the poison queue's number. And one of the things I want to do is look into, maybe investigate getting a second worker that is purely dedicated to the poison queue. But right now that wouldn't be ideal, because the idea with the poison queue is that you need to be an engineer and take a look at the assets coming through it to figure out any problems, and we'll talk about some of those problems when I get there. Next to that is this graph, which isn't that useful, but I've got it here as a sort of like a thought experiment, or sort of to look at it and figure out what we want to do with additional metrics. So you can see here that we've got the number of started, successful, and failed. The gap between started and successful is the same as the gap between failed and the bottom of the graph, which is just an interesting mathematical thing. But you can see that as all the numbers increase, as do the failures. So we have something somewhere that is causing a growing number of failures. That's also expressed by here being 4% and by this poison queue being quite having that flaw to it. To look into that more, you can see we've actually broken out some of the data here. So this is the bitmap compression method. So BC1 here means block compressed. I don't know exactly what these means. I want to put them on a wiki at some point so that people can see what they are. I do know here that ETC2, these are the mobile variants, so we do a lot of those. I don't particularly know why we're doing so many of them, but whatever. Maybe we weren't doing them properly before or something. Who knows? We've also got the compression of mesh colliders. So the options here are LZ4 or LZMA, both very popular compression algorithms for that type of data. And then we've also got the task types here. So bitmaps are the compression into these. Bitmap metadata we just talked about as well. Mesh variant, not quite sure what that one is. I'll have to look into what metrics we can maybe pull out of that, because we don't have the same as the mesh collider. I think actually mesh variants are on the mesh collider ones. I'm not entirely sure. I'd have to double check. There's mesh metadata as well, which is the same as bitmap metadata, but just for meshes, and the same goes for cube maps as well. Periodically, we do have to do stuff to shaders as well. You won't see much there because we have such a limited amount of shaders. So there's the metrics. What I wanted to do, though, is I wanted to figure out, hey, like, what's going on? Like, what are these failures coming from? And this is where you can actually start using these metrics now that you've got them to figure them out. So I wanted to show you that live so you can see how we would do it. So I can come in here, and this is Grafana, by the way, and it's hooked up to a Prometheus instance. And if I go here to the failed tasks, I do that by typing in failed, and you'll see it drops down to failed tasks total. And then I can say, hey, show me the failed task. This is going to be a graph that is like really complicated. But if we mouse up here, we can read this and we can see, hey, BC1 LZMA has a high number of failures, and that's a bitmap variant. So let's do a label filter of type equals bitmap variant, and then run the query again. And you'll see here that we've got rid of anything that was failing that wasn't a bitmap variant. What we're going to do now is we're going to do an aggregation where we're going to sum, and we're going to sum it by the label of type. Oh, no, actually not type. It needs to be compression. Yep, here we go. So now what we've got is specifically the bitmap variants that are failing, and we can see on a graph which ones are failing. And we can instantly see, and let me just make this a little bit easier to see. If I do this, this, and there, you can kind of see it a little bit easier. You'll see here this yellow line is BC1 LZMA. So I hazard the guess, like a lot percentage. I don't know what percentage that was. I could figure it out, but that would require taking a look at the successful BC1 LZMA tasks. But we have a lot of BC1 LZMA failing, and that's cool. We can look into that now and be like, cool, let's look at that part of the code. Let's figure out what's going on. Let's look through the logs of the worker and interrogate it. What one's running out here? LZMA as well. So we're seeing a pattern here. It's mostly LZMA that's having a problem. That's LZMA as well. Yeah, so any BC LZMA is failing at a higher rate than I would say others are. I would have to look into that more with like a better graph to see if like the failure number here is as drastic as it looks. Like, the 400 is a large number, but let's say 2,000 are succeeding and 400 are failing. That's a different magnitude than if 400 were failing and 2 were succeeding. So I'd have to look at the success metric on top of that. I can actually do that. I don't want to do that though, because there'll be too many lines on that. Finally, there's a little more peek behind the curtains. This is Kane, which is the Sveckenbox one. It's running the poison queue. And you'll see lots of stuff here. But you also see that it keeps crashing. And it's crashing due to a PAL SEH exception. By my understanding, and I've just literally just Googled that phrase, so you can go ahead and do it myself, but yourself, PAL SCH exception basically means um, the the running program has escaped so much, so sufficiently from the like .NET runtime structure that the whole thing just like dumps. So you can look that up. But basically, if you look it up, most .NET people say like, "Hey, it shouldn't be happening." There's a couple of GitHub issues where there were problems in the .NET runtime itself that were fixed to cause this exception to go away. But I think that was like SEHA, so like a different type of exception. What we need to do for this particular issue is we need to grab and find out which of these assets, and I'm not sure which one it is. I mean, it's certainly not this one because that's a convex hull, but one of these assets is causing that. And so what we'd do is basically turn everything off and say, just process this asset. Like I would maybe download it. Maybe it's this one. I would take this file and I would stand up a standalone piece of code that takes that file and tries to do something with it. And then we can step through it from a sort of code dump area and take a look at where it's failing. It's probably failing somewhere in native code, which is interesting to see. But there you go. That's one of the failures. When this occurs, it interrupts the processing that the worker is doing, so much so that it's leaving behind ghost temp files. Whenever we compute a variant, we download a temp file and we store it in the temp directory. And when we're done computing that asset, we then remove that temp file. But if it crashes, we can't remove that temp file because we've crashed. So temp is getting full. Solutions to that one, of course, are to fix the bugs, or what I've got displayed here, which I was talking about in our previous take, which is we can put like all the files for the asset worker in a separate folder. And I would want to add a unique identifier that, or whatever it might be, just so that we don't trample on any asset workers if we're running two on the same machine. So each one would have its own folder in temp, and then we can just clear that folder on startup. But that might get problematic as well. So we should just go ahead and fix these bugs. So you can see here, there's another type of bug, which is cannot serialize empty convex hull. These keep coming through. And so what we need to do is figure out, like, why is this convex hull empty? Is the mesh empty? If the mesh is empty, then we can just say, hey, don't serialize an empty convex hull for a mesh that doesn't need one. But maybe there's an error going on and this convex hull isn't actually empty. Maybe the mesh isn't actually empty. So we'd need to, again, look into it. So we'd have to, like, download this variant and take a look at it. And again, run through that. So this is just going to keep going. You'll see there's another issue that I'm trying to... Yeah, there's this one that comes up sometimes. I've got to look at that one more urgently because R8 was a problem, not this Christmas, but like last Christmas. I mean, like 2024's... No, 2023's Christmas, yeah. There was a problem with R8, so I've got to look into that one. But there's also... I don't know, maybe it's easier to see. Yeah, here it is. Generated variant file doesn't exist. What this means is that we've generated a variant, and then for some reason it doesn't exist on the file system. So again, that's something to look through. This happening, this exception, will mean that this asset, whatever it is going to be dumped into the poison queue, and it doesn't really need to. This is like a technical issue with the queue that's happening. So it's going to be important to take a look at that. You can see, though, that this is the main worker. You can see it's processed 29,000 jobs, and this is like a scroll back away from where it actually is. Let's see where we are. Yeah, 29,677. When it slows down like this, it means there are no more jobs coming in. And that's one of the confusing things as well, because like if we look at the dashboard here, you'll see this floor here, and that's why it was confusing for a bit. It's like, why is the main worker not doing anything, but we've still got 6,000 assets in the queue? That's because they're all in the poison queue. So there you go. Just thought I would explain a bunch of stuff. Hope it's interesting, and I'll speak to you soon.